The next thing that we're going to want to do is we're going to want to take this information that we have and see if we can do anything with it that is slightly more interesting than just color coding everything and making things, annotated in that sort of way. We want to actually analyze these images and do something interesting with them. So what we're going to do in our next box down is we're going to create something called a histogram. Now, for those of you who aren't familiar with a histogram is basically a bar chart that separates a range of values into buckets or into groups so that you can see where things are. And you see histograms all the time. Basically, if they ever try to say what voting patterns are like or health patterns, and they put everyone into under 18 or between 18 and 36 or 36 to 55, those are different buckets of data. They've just put all of them together as opposed to graphing it individual age groups, and you get kind of a bar chart. Now, what we can do with the programs that we have initiated is we can create a histogram of the different colors that exist within our entire image. And we're going to create this together. And then once we've created it, we are going to sort of walk our way through it so you can kind of see what all the elements in it are. So the first thing we want to do is this image has now been modified or tainted with these little bar stripes. So we do want to start from scratch and do it again where we have a new image variable, or we rewrite the image variable with our original image once more. And then we're going to create a very simple histogram. But in order for our histogram to sort of have the information we want, we need to give it a couple of values. So the first thing we're going to do is we're going to create a histogram for red. And that's another thing that you have to understand is that because a graph is only a two-dimensional representation, we can't make a two-dimensional representation of a three-dimensional object in that way. We can overlap them, but it would be very, very messy and sort of difficult to read. So we're just going to do it with each individual channel. So we're going to do a histogram for red, and then a histogram for blue and a histogram for green. So our histogram for red, we are going to have two different labels so that we understand what's going on. The label across the bottom, or our X label, are going to be our values. So anything from 0, which is black, to 255, which is complete, pure, full blast red. And our Y label is going to be frequency. So that's going to be on a scale of 1 to, I think, about 1,000 in this case. How many times that color of pixel, that color of red, appears in the image. And then what we want to do is we want to tell it what part of the image, what slice of the image, or what cropping of the image we want to use. So we want to plot hist, which is create a histogram. It's a method that already exists within Matplotlib. The image. And again, we want to do all of the Y coordinates, all of the X coordinates, and then we just want red. We just want 0. And then we want to show the entire image, of the graph. So instead of doing IMShow to show the image through Matplotlib, we're actually going to go back to just PLT show to show our graph. Now, when I hit enter, this is going to take a minute. And the reason that is this is an extremely high resolution image. It looks very small on your screen because Jupyter Notebook has shrunk it down, but it's actually a 2K image. So it's going to take a minute to run on my computer, at least. It might take very, very quick or very, very slow on your computer, depending on what type of processor and what kind of memory your computer has. But we'll just take a moment and take a breath and see how that works for us. So as long as that asterisk is there, it means it's running through the program. There we go. And we have our histogram for red. And as you can see here, it's not completely an even distribution. The very, very darks are rather limited, and the very, very bright reds are kind of limited as well. And you do get a couple of spikes, but you can kind of see that there are these clusters of different red tones. And in fact, they're actually very clearly defined where there's no pixels sort of between these different clusters, which is interesting in and of itself. So it seems to be that there is not a complete full range of tones. There's actually 1, 2, 3, 4, 5, 6, 7 kind of groups, main groups of reds that are being used that are noticeably distinct from each other. If I change this, actually I'll leave this up. If I go to a new one and I do the same thing, but I change it to blue, and I change this to 3. Again, it is going to take a moment. Oh, sorry, 2. It is going to take a moment to process, but then we'll be able to compare these two histograms and see how they differ or how they're quite similar. While it's doing that, does everyone understand the code that I've put in here? So let's just leave that. There we go. And the histogram from blue is similar, but as you can see, whereas there's some very high value reds towards the end of this image, you do not have that same kind of high value blue. Blue kind of tops out at 200, which is still 80% of the way to full, but not quite as much as red. Red is much more likely to have a full value range. It tends to be lower. So the blues that are in there are less significant, which actually makes a lot of sense if we return to this image. Taking out the blues was not that disruptive, or not as disruptive as taking out the reds. And you can kind of see that image analysis going on there. So why would you want to do this? What kind of purposes might this serve? Well, there's a lot of times when you are looking at an image where you're trying to pick up very fine detail, very fine differentiations or very fine distinctions between shapes or objects or compositions. If you were trying to attribute certain images and you want to do it by the palette, you would also use these histograms almost like fingerprints to see what types of things are available, what types of color are. Now, that, of course, works better in analog images where, you know, having access to certain pigments or paints might give you a clue about their origin, as opposed to a digital image where, you know, we can have any of millions of colors if we so choose. But it can be very useful, especially if you're doing things that aren't even necessarily like paintings or landscapes. If you were looking at signatures, for example, or manuscripts, and you want to look at the ink, it can be very, very useful to be able to manipulate the image or look at the different tones. I remember very clearly back in, chemistry class back in secondary school, taking lots of different black inks and expanding them out, watering them down to see what they actually were, whether they were made of blues or reds or things like that. And this is the same sort of thing. You can actually do quite a lot of forensic work by breaking up these images into their components, with the caveat, of course, that it also depends on how well it was scanned and brought into the digital world. You don't want to be sending anybody up the river based on this sort of information without doing a little bit of due diligence in that regard. Okay, so now that we have our two histograms, perhaps you're thinking, well, that's all well and good, but what if I want a more overview image, like not just the reds, not just the blues, but sort of all of them together? Well, one way that you can do that is by turning the image first into a grayscale image, which you may want to do anyways. A grayscale image is really useful because unlike a color image, it only has 2 dimensions. So everything is either black or white or some sort of shade of gray between the two. So you can have a histogram where it is simply those values. Now, turning an image from a color image into a grayscale image is a little bit difficult. There's a couple of different ways you can do it. Now, the way that most people like to do it, and I will just start with a fresh copy of our image again, is to show our image and only show the red channel, and then use a gray color map. And if I do this, let's see here. It's an E, it's the British way. There we go. So if we do this, we get this image, which is a grayscale image. It looks like the School of Athens, but as you can tell, it's a bit of a cheat because, and thank you for that hint there. It's a bit of a cheat because this isn't really grayscaling the whole image. It's actually just grayscaling the red channel. It's not doing it properly. So what we want to use instead of this is we want to use one of those other libraries we had at our disposal, which is ImageOps. Now, ImageOps is a program that's going to do a little bit of mathematics for us. And it's going to try to average or add together a certain proportion of red, green, and blue across all 3 slices of the image to give an approximate grayscale. So the way that works is if you type in gray image, that's going to be our new variable. And the program is called ImageOps. And the method is called grayscale. And we're going to turn that image into a grayscale image. And what we're going to do is if we show that image, show just on its own, you're going to see that psychedelic color that I was talking about previously. And this has, for some reason, not worked. Let's see here. Sorry, there's been some libraries that haven't gone completely through because of my my restart. There we go. Oh, yes. Okay. I apologize. Sorry, because we're using ImageOps, we have to read the file in a different way. So rather than using the Matplot image reader, we're actually going to load it up into a different function, which looks like this. So it's image.open. It's using the same set of libraries we did beforehand. It's just formatting the file in a slightly different way so that we can bring it up. There we go. So as you can see, this is the slightly psychedelic version of the School of Athens. And the School of Athens here is represented by black being essentially very, very, very dark blue. And it goes up through the midtones, which have been done as green, and the white or the high tones, the highlights, have gone into yellow. And on its own, this can actually be very useful because it creates a very high contrast image that basically just tells you the value of the image as opposed to worrying about the actual tone and color. So if you just want to see where all the shadows are and where all the highlights are and not let yourself get optically confused by the various tones of the different colors, this can be really, really useful on its own. But it's a little bit not as great as we want it. So we want to try maybe to go to CMap and go to grays. And that will give us our grayscale image. And that really just lets us see the grayscale going forward. Now, what we're going to do is we're going to save this so that we have it as a saved file, as a grayscale file. But we don't want to have these little numerical axes. We just want to save the image as it is. So what we want to do is we want to turn the axes off. And then we want to save the figure. Now, this is going to save the image in that same working group, that same working folder that everything else is saved in. So save figure, gray image.jpg, and bbox inches equals tight just makes the white space around it a little bit smaller so you don't end up with an image with kind of a border around it. So if we do this, I have forgotten all of my strings. Okay, so save fig, the name of the file goes in a string, as does the word tight for the variable bbox inches. So this image is now saved. So if I go back into my working directory, I do have it there that I can pull it up and use it. And the image is about a, what is that? A 14th of the original because it has a lot less information. It's just got that one level of information. So if we go back to our histogram program, and instead of doing the blue, we change original image into gray image. And then in this case, it's a two-dimensional object, so we do not need to have that level. We can just do this. Oh no, it still wants it. It's just made the same on every single level. Okay. It will run through it. Now I put 0 in here, which is the red layer, but because we made it grayscale, it's the same for all three. Now, if you look at this, what you can kind of tell has happened is that it has basically used the highest level value for every single color. So if green was the highest value, it's made that the high value. If blue is the highest, it's used that. And what it's ended up having is that all of those really high value greens and high value blues and high value reds have all ended up together, which is why when we look at our image, it has this ghostly white. So the image ops grayscale is one way of turning the image into grayscale. There are other ways of doing it manually where you actually multiply the red by a certain percentage, the green by a percentage, and the blue to get a more realistic version. But this is a very simple, quick and easy way of turning something into a grayscale image for analysis. But it does create these little artifacts. But on the other hand, it has balanced out our reds and our blues by kind of combining them together to give us a more even spectrum of 0 to 255. Okay, so the final thing that we're going to do today is we are going to look at the image and see if we can't crop and zoom in to different parts of the image in order to examine them more in more detail. And then you can run those same kind of analyses on them that you did for the whole image, because sometimes a histogram for the whole image is not going to be as useful as it is for a certain aspect. So the first thing that we're going to want to do is we're just going to bring up a version of our entire image just for reference. So just so that we can see what we want to do going forward. And I'm going to make this just a tiny bit smaller so I have a bit more room. So we have our image here. It's in full color again. And we have our coordinates, pixel 0 to pixel 3000 odd, and pixel 0 to pixel 2000 odd. And what we're going to do is, if you want to show just a small part of the image, what you can do is you can crop the image using the image crop functionality. Now, if you just do on show and you did 0 to 500 and 0 to 500, and then run this, it's not going to work. So while you can manipulate, while you can manipulate an image, it's not behaving today. My apologies, it's been a bit of a longer day than I thought it was. Right, so while you can use this to add color bars to the screen, like we did before, it's not going to present the image in its entirety that way. So first thing that you have to do is you have to actually crop the image down to a smaller size. And the way you do that is with the function crop. And this is a little bit confusing, but it's a double set of parentheses. And you have 4 variables, which is how far left do you want to go, how much from the top, how much from on the right, and how much to the bottom. And what you have to kind of think about it is, if I were drawing a sort of square from here, what is this leftmost number and what is this topmost number? So like 500 is the left number and top is the 250. Down to here, it would be 1750 is the bottom number and 2500 is the right number. So if I go here, I'll just make this a little bit easier. So if I start at about 500 on the left and 1000 on the top, and I go to about 3000 on the right and about 2000 on the bottom, that should give me roughly the section of the image that has the individuals shown. And again, I want to save that as its own variable, IamCrop. And then if I demonstrate this, you can see it's cropped it down to just this section. So what's important here is that the original image still exists as IMG, but image crop as its own variable has an entirely different set of data. It only has the data from that cropped section. Now, the problem with doing this, if you'll notice, is that these numbers do not match up. So this is the 1000 or so pixels of this image, this cropped image, and this is the 2500 of this cropped image, but it doesn't relate to this section here. So if you want the numbers to relate, you're going to have to create some sort of more systematic way of doing this. So rather than just doing this on its own, we can create another small program. Now, I'm not going to put this into a function, but you could do, and it would work just as well. And I'm going to ask for each of these variables in turn. the left, the right, the upper, and the lower. And that way I'll be able to go through this very, very quickly every single time. Now, there is a int in front of each of these inputs. Does anyone have a guess as to why I would do that? Why would I recast these as integers before I pass them on? Yes, because they're numeric values. When we do this here, they're turning green because these are integers. As default, input usually takes a string. So if you actually use the input and you want a number to come out that's actually, you can perform mathematical functions on, that the computer knows is a number and not a string of a number, you have to let it know that. Then we want to replace these numbers. So as I said, it needs to be left, upper, right, and lower. And then we want to change our axes. So we want the bottom axis, or the x-axis, to use the left number as the leftmost number and the right number as the rightmost number. And for the y values in our square brackets, we want to use the lower number on the lower side and upper on the upper. So this is a little confusing in that this is the it doesn't look like it's the lower number, but it's the way of the lower part of the image, not the lower numerical number. So we ask for those 4 numbers, it creates our image with it, and then it will present it with the correct elements. So if I run this, and this time I'm going to use, so what did we have? We had about 1,000. Oh wait, that was the wrong way. That's okay. 1,000 again. Right, we'll put it to about 2,000, and lower, we'll put it to about 2,000. So this will give us an error message, which is, that's an N instead of an M. We'll try this again. So 500, 1,000 to 2,500 and 2,000. And the reason this has not worked is I'm not 100% sure. So let's try this again with different values to see why it doesn't like. There we go. I've probably just put in numbers that are beyond what it can handle. So 0, 0, 50, 100. Yes. So as you can see here, this is now giving me numbers from 0 to 500. So it's representing just this part of the image, and 0 to 50. So just this tiny little strip. So if I think about it very carefully, these 2 individuals there, does anybody happen to know? Oh, sorry, you've got a chat message. Yes, so it's I am crop. Let's see here. Image.crop. I am crop. So for these operations, you have to open it with the other creator. So it has to be the image.open. So yes, so you can see this. So does anybody know who these 2 individuals in the center are? Either who they represent or who they're actually images of. So they're actually, it's supposed to be Plato and Aristotle, and Plato is actually Leonardo da Vinci is who it's modeled on. So it's not liking when I'm using these larger numbers, and I think part of that might be just the same thing that's going on here, where I need to refresh my image. Yes. So if we go here, we can now see that I've cut off the individuals that I was actually interested in, which are these two over here. And we have our grumpy little philosopher down here whose name starts with H and is completely out of my mind at the moment, but he was a very stoic individual. So yes, so this particular function basically allows you to go through the image over and over again and create different crops of it. So we're going to try that one more time. Left of about 1400, 1000, right of about 1850, and lower of about 1500. Perfect. I will get there in the end. So we've got Plato and Aristotle arguing in the Academy of Athens. Now that we've got just these two individuals here, we can run the same sort of analyses that we've done on other aspects on just these two. So if I wanted to run my red color images on just this section, I would be able to. So instead of running it on image, I run it on image crop. Is that what I called it? Yes. And I want just the red layer. And I want it in reds. And this is when you don't want to mix and match your various libraries. But the idea is that if I save this image and brought it back up again, I would be able to run my analyses in it as well. Or if I had done it all through the plot image library, I would be able to do it as well. So there's lots of different ways that you can run these sorts of analyses on these images and zoom in further and further and further. So if I just use this, I should be able to yes, this is a different standard, and I'd have to look it up to see what it is. I'm very, very sorry. But you are able to run the same images through the system again and again and get different kinds of analyses on them. The next one that I want to do, I will actually have to save this. So I'm going to do the same thing I did previously, where I turn the axes off. And then save the image to cropped image. Did not mean to do that from the beginning. Let's just cancel that out. There we go. So now I have cropped image as a file on my computer. And what I will do is I'm going to show you one last thing for today, which is something called masking. Now, masking might be something that you are familiar with in other fields or in other situations. But what it actually entails is the idea that you would take a certain value, a certain level of an image, and you would remove that from the image in the same way that we did previously with our strips of color. So if we have our image, we are going to apply it. Now, this is going to be very, very similar to what we did with matplotlib, but we're going to use a different library. And the reason we want to do this is because this will allow you to create more complicated masks in the future. Just so that you're aware of the syntax and that you're aware that it's out there. But for the moment, we're just going to do red. So if we have our image, and we're going to use the library image.io, and we're going to read our cropped image.jpg. The next thing we're going to do is we're going to create a mask, and this mask is going to remove everything on the red at a certain value. So on the red, cross X and Y on the red, and then you're going to use less than or greater than. So what I want to do is I want to mask everything that is under 200 value. So all the very dark reds, all the very deep, almost black reds, I want to remove those and only leave those very high scale reds left in there. I'm going to then apply my red mask to my image. And I'm going to tell it what I want it to be in value. And I want to take all of those things that are under 200 and I want to turn them to 255, which is going to turn them white. And then when I show my image, there we go. So we have our cropped image here. And in this case, all of those very dark reds, things that were not maybe red at all in the image, they have now been turned to white. And what this is doing is it's not taking the reds out and leaving the blues and the greens. It's actually replacing all three layers of the image with white. It might make a little bit more sense if I turn it to black instead. And this is basically putting a mask or putting masking tape, I guess would be a way of thinking about it, over any part of the image that has those low red values. If we do it the opposite direction and do it with anything that has a high red value, you can see that all of these areas are actually heavily dependent on very high levels of red to make the image. That doesn't seem to be very obvious. This is like actually a blue cloak, but it actually contains a lot of high value or almost white bright reds in part of that composition with the blues and the greens. And this can be really, really useful if you're trying to remove noise or you're trying to clarify different aspects of the image. So hopefully that makes a lot of sense for you. What we've done today is we have learned how to download and load in imagery. We've used a small program in order to pull out the red, the green, and the blue channels. And we've also displayed them here so that you can see how these affect the image material. In terms of analysis, what we focused on is creating numeric histograms so that you are able to see sort of what the distribution of the red, green, and blue channels are for your image. We've also looked at some tools and some limitations of those tools for turning color images into grayscale, as well as how to crop images and display them in a way that's useful for that cropped image, and how to mask certain colors or certain areas out of your image in order to focus on certain points, in order to really draw the eye or draw your attention to certain aspects of your image. We're going to stop it there for today, but I do hope that this has been useful for you. So thank you all for coming, and I hope you found this useful.